Hi, I'm PJ. Since all of you here Monday or on Girls of Steel, you all know me already, but I'll give the spiel for the recording. Um, I am a Girls of Steel software mentor. I've been doing first since I was in high school, a long, long time. So this is part 2 of my Intro to FRC programming workshop. So, tonight we're going to be talking about control systems. It helps if you know a little bit of Java, and we're at some of the previous meetings that either I or Sarah hosted, or watch them online, but it's not totally mandatory. And today we're not actually going to be writing any code. It's all going to be what we call tuning. And we'll go into that in just a minute. For the 3 of you that were here on Monday, do you want to take any time and talk about what we did Monday? We could maybe carve out a little bit of time to finish up some of the code lab that wasn't finished, or we can just jump right into PID. Silence means keep going. Okay. I'm doing this at a different place than I did my previous one, so I only got one screen, so I'm probably gonna be jumping around a little bit. Do you see my presentation? Yes. Okay, cool. Okay, so today I'm going to be talking about control systems, the common ones that we use in FRC during the season. There's many different types of control systems, but for the most part, it boils down to 2 main groups for us. So what we're going to talk about what a control system is, what's the goal of it. We're going to talk about the easiest control system. You might not be able to truly call it a control system, but dead reckoning. We'll go through what that means. I'll give a quick overview of what PID is and how you can tune it. WPI has a nice little thing that you can play around with now as an example. I'll also talk about what motion profiling is, which has many benefits over standard traditional PID. And then I have another code lab for today where we will go through and just tweak knobs until we get the robot acting like how we want it to work. So what is a control system? The basic idea is that it is something that allows us, we have some goal in mind that we want our shooter wheel to go a certain RPM so that our shots are more consistent. Maybe we want to drive off the auto line in autonomous, or we want to do a fancy path so we can score multiple balls, whatever. We need some way for our robot to do that, right? And the way that we do that is a control system. So every control system, besides dead reckoning, uses sensor feedback. So the sensors that we talked about last meeting, encoders, gyroscope, whatever, we'll be reading values from that and then figuring out what's the best next step. What should we do this loop to get to our eventual goal? And like I mentioned, there's many ways that you can do this, but we'll focus on PID and motion profiling. Over here is one of my favorite GIFs of the cheesy poops and whatever the castle year was. There's a lot going on under the hood to make that work, to make their turret stay aimed while their robot twists and turns like that. So ideally, that's what you're hoping to shoot for. So when we say dead reckoning, that essentially means that you're not taking any feedback from sensors. And usually the way that you accomplish that is by using timers. So you can imagine for a simple get off the line autonomous, maybe all you have to do is like drive backwards for a second at half speed. And that will work perfectly fine. Depending on your battery voltage, driving a second at half speed might get you 3 feet, or it might get you 2.7 feet or 3.3 feet. But as long as those get you off the line, who really cares? It's super simple, super easy to write. So, that's always the first autonomous mode that I have my kids write, just in case everything's broken, everything's terrible, our encoders are unplugged. Not that works in a brushless motor nowadays, but if everything goes terrible, it's nice to have this in your back pocket just the easiest way to write in autonomous mode. And now for other simple things, if you have a big time budget, doing timers makes sense for that too. Like in our robot this year, when we were shooting balls, we had our little hopper where we're storing balls and transferring up to our shooter. We would just run that for like a second or whatever it was. We might have shot the ball at 0.4 seconds and wasted, the next 0.6, but that was the easiest way to do it, so that we didn't have to rely on our ball sensors, our beam break sensors, or anything like that. So there's definitely times when doing the timers has very little ill effect on your robot. So where was I? I got lost in the chat. Okay, so now why would we want to use sensors? Why would we want fancier things? Well, this robot can kind of give you an example that's over here in the GIF, right? Like, who knows what happened? They might have had an encoder unplugged, or they might have written bad software, but for whatever reason, they're just driving straight on off the field, right? At this probably week 0 event or off season thing or whatever. So ideally, you don't want to do that. You don't want to be crashing into walls at full speed if your time or motor power is not perfect. So that's why we eventually want why we want to use sensors for feedback. And if you think, like, if you have a really precise shooter that's shooting at an RPM, and maybe you have a lookup table so you know when I'm 3 feet away, use this RPM, you need to hit that RPM pretty good, otherwise your shots are going to be inconsistent. So there's many, many reasons why we want to do fancier stuff than this. So the most common way is called PID. And under the hood, it's sort of calculus adjacent, like I and D are for integral and derivative, which are calculus terms. But you don't really need to know calculus to tune one of these and hook it up to your robot. But the overarching idea, no matter what kind of PID controller you're using, is that you have some goal, some endpoint that you want to get to, some velocity you want to get to, whatever. You have some goal, and you have where you currently are, and you use the error between those two values to decide what you're going to do next. So to break down the terms of PID, P stands for proportional, which is like, the bigger my error is, the faster I'll go. So as I get closer, I'll naturally slow down. And the math for this is just error times some knob that will tune, called P. Sometimes KP, you'll see a couple of different things if you look at other people's code, but they're proportional term. I did this out of order because this is normally the way that we would tune the first 3 at least. Derivative, if you know your calculus, that's the slope of your line. And basically what that does is you want your velocity to slow down as you get to your target. So it's kind of like a brake. It's like, oh my God, I'm almost there, I got to slow down. The P part will just go naturally, linearly, but the derivative will look at how fast you're getting there. And based on how fast your change in error from the previous loop to this loop, and it will slow down. One thing that I like to say for this is, imagine if I told you to stand up and run across your room and touch your nose to the wall. You're implicitly probably going to do some PD controller to do that. You're going to start out at a full-on sprint, right? And as you get closer, you'll slow down. And maybe when you come up to the wall, you'll put your hands out to kind of brace your impact, because you don't want to smash your nose and break it, right? So that putting your arms out and helping you brake, you can think of that like the D. The middle term is called integral. So what that's doing is it's adding up your error over time, just like what an integration does. So basically what that does is, like, kind of, if you're stuck, this error will be building up, and eventually it might become so large that you'll actually move. It'll give you a little bit of an extra nudge. For practical purposes in FRC, we don't really use I that much. And in all honesty, you can get away with just a P controller in most situations. But if you need a little bit, you need to cut a little bit of time out, make it faster, then you might want to do a PD. And I left F to the bottom because first I'm going to ask a little question. If I'm doing a position controller, and let's say I'm at 5 feet and I want to go to 0 feet, once I get to 0, what should I do? Should I stop or keep moving? Or let me start over. If I'm at 5 and I want to go to 0, what should I do? Should I move forwards, backwards, or nothing? Should be an easy question. I did say 5 to 0, so I guess it would be backwards. Yes, you move backwards, right? Now, let's say I did that, and now this loop, I'm at 0. Do I want to go forwards, backwards, or do nothing? What kind of power should I be giving to my motor? Nothing, right? Yeah, exactly. So in a position-based controller, when we get to our goal, when our error is 0, we want our output to be 0. Now, if it's a velocity that we want to do, like we want our shooter to go at a certain RPM, so they just hit the button, I'm at 0 RPM, I want to go to 1,000. Should I spin forwards, backwards, or do nothing? Yes, forwards. We need to get this guy spinning up. Okay, so spun up, spun up, spun up. Now I'm at 1,500 and I want to be at 1,500. Should my motor be spinning forward, backwards, or stop? Anuba said same spin, which is exactly right. Right? If we stopped it, then it would slow down, and by the time that our gets in, it'll be going slower than we want. So velocity, as our error down to 0, we still need our motor or whatever it is, but we need our motor to keep moving, right? So the way that we do that is we add this F term in. So all these other 3 guys, we're looking at our error, right? We're reading an encoder or gyroscope or whatever sensor it is and trying to drive our error down to 0. For a velocity one, since we want to keep going, we say, I bet there's a speed that gets me pretty close. I bet there's some value that I can multiply by my RPM that gets me like in the ballpark, right? And that's what we call feed forward. So as opposed to doing feedback and reading an encoder, feed forward just takes our goal and multiplies it by KF, and that'll give us a baseline for how we should move. So if you discover that 6 volts gets you 1,000 RPM, maybe it's like 990 and the battery voltage makes it a little bit higher or lower or whatever. But if we figure out that 6 volts gets us 1,000 RPM, we can do math and do 1,000 over, do 6 over 1,000, and there's our KF. And that way it works. If we want to go 2,000, we would multiply 2,000 times whatever our KF is. And that gives us a nice baseline that we should get pretty close, no matter, without even looking at the sensor. That's really cool to watch when you first start doing your driving. If you do a velocity controller for driving, because you'll get like within a couple inches without even looking at the encoder, just by using feed forward stuff. So feed forward in a velocity controller does the vast majority of the work. Like 90% of your control effort, what you're giving to the motor, should come from F. But then after that, then you can start adding P to get it, maybe getting there quicker or balance out those battery voltage errors. Yeah. Now, I mentioned one thing here. You can also add in arbitrary offsets to your control effort. One example would be like for gravity, right? If you have an elevator system, it's going to go up slower than it is coming down, right? Because of gravity. On the way up, it's fighting gravity. On the way down, it's getting assisted by gravity. So what you can do is you can say, well, you can empirically play around with your robot and say, it takes about 1 volt to cancel out gravity. Like if I give the motor 1 volt, it's going to stay exactly where it is. If I give it no power, it's going to come slowly or slam down to earth. But if I give it 1 volt, it will cancel it out. Mechanical people do a similar concept, right? If you have an elevator, like an elevator in a hotel or whatever, they actually have a counterweight on the elevator that weighs the same as the elevator box, such that when the elevator goes up, the weight goes down, and vice versa. That's called counterbalancing. So you can add arbitrary things to like sort of counterbalance in software. I always like the mechanical team to counterbalance it as much as possible before we have to do stuff, but you know, you take what you can get. So what if I had an arm like this? What kind of thing would we have to do to compensate for gravity there? If I say, let's say this is 0 degrees and this is 90 degrees. So you can think about our intake that we had on Girls of Steel this year. Somebody said go up with more power, which is true, right? We want to add more power this direction than we do when you go down. But is there any kind of equation? Because when we're here, this has a huge force acting on it, right? So it's got to fight a lot of gravity when we're at 0 degrees. If we're at 89 degrees, it doesn't have as much gravity to fight anymore. To go from 89 to 90 is way easier to go than from 0 to 1. Any ideas? Anybody take geometry? I imagine is when they teach it. Cosine, exactly. So from a software perspective, I hate arms that do this. Because in order for us to make our control system, we have to read from the encoder, hope there's no delay in it, multiply it by our gravity offset. But yes, exactly. So, you know, PID systems, I forgot to mention this, PID systems work well with linear systems. Like a drivetrain, it goes the same as it goes forward as it does backwards for the most part. And a motor curve isn't totally linear. It's got a little bit of stuff at the ends, but for the most part it is. So to work with things that are non-linear, like an elevator fighting gravity or an arm that does this, we have to compensate that for that. Otherwise, it's super hard to tune them if you're not trying to make them linear. So if anybody also does mechanical stuff, try use a pneumatic for this if you can. So when we go tune these things, it's never going to be perfect. Like it's impossible to hit our goal right on the nose, right? If we tell it to go a foot forward, did it go a foot and 1 hair forward? It's impossible to get it right on the nose. So some questions that we have to ask when we're figuring out this stuff is like, can I overshoot? Can I go past my goal? If you have a delicate mechanism and you're picking up something on the wall, you don't want to drive 3 inches past your goal, right? You'll smash your intake up or whatever. But if you have a shooter wheel, a flywheel, you know, who cares if it goes a little bit faster than it should for a second if it settles down in the right spot? Can we make it faster, and should we make it faster? That's always a constant dilemma. Like, how close to the limit do we want to push this? And the closer you get to like maximum efficiency, it's like diminishing returns for how much time you're spending on it. So there's a balance of how much time do we have to tune this versus what kind of quality can we expect out of it. So always push for as much robot time as you can. How close is close enough, right? Do I have to be within 1 inch of my goal? Can I be within 3 inches of my goal? You know, 1 degree for shooting a ball full field versus, you know, I could be off by 10 degrees either way to pick a ball up off the ground. Those are things that you have to think about and figure out because that will impact how you have to tune your system. And then you should always do all of this testing with a dead battery and a fresh battery because your mechanisms will respond differently. Hopefully your PID is canceling out a lot of the difference that comes from a different battery voltage. But you always want to do that. You always want to make sure that it behaves the same in autonomous mode as it does in the end game, or as close to as possible, at least. And a really, really annoying thing is that if you're doing multiple letter controllers, they tend to have a big effect on one another. So you can get a nice P controller all perfectly tuned, and then like I want to dampen some of this oscillation, and then it could just drastically affect everything else. So a lot of times you're going to be sitting at your computer tuning knobs, watching an arm do this for 2 hours, and just trying to, make it the best that you can. So if you click on these links, WPI, WPI is not landed yet this year, but it will be in the docs for the upcoming season. They have a little tool that you can play around with and tune something like this. And it's got nice little visualizations, much better than my Code Lab does. But who wants to try tuning a shooter wheel real quick? I think here's the actual part of it. Yeah. I'll send this link in the chat. Okay, so does anybody is this the part I want? What do you mean by an arbitrary feed forward loop? So usually you would get those values from sysid. Yeah, so like ideally those are measured empirically, and then you just take them as truth. You don't really mess around with those numbers. That's relatively new, and that's how I've been dealing with it, is just taking them as truth and then tuning my parameters using those base things. And for this tool specifically that we're looking at, it's more just for demonstration. Doesn't tie into sysid or anything like that. So if we wanted to tune this, what kind of control system do you think this flywheel is? Is it a position or a velocity controller? So if it's a velocity controller, what should we tune first? Who's going to be our heavy lifter? Traditionally called KFF, that's what I've been saying. Here they have it listed as KV for velocity, but same idea. All right, somebody yell out a number. I should have said this before. I prefer if you just unmute yourself and talk, especially now that I'm doing this on one tiny laptop screen. It's easier for me to see that than the chat. So when we do this live tuning stuff, just unmute yourself and yell out a number.
One.
Let's see what 1 does. So, I should talk about what these plots are, right? So in the blue line here, this is our goal. Our goal, we also use the term set point a lot for that. You'll hear both of those used interchangeably. And this red line here is the actual measured output from the motor. So it looks like it's going way too fast, like 3 times as fast as it's supposed to. So what should I do to this number if I am going too fast?
0.1.
0.1. Yeah, a general. Do I have to hit enter? Still, that didn't change, which is weird. Okay, it was still just humongous. Yeah, so when you're tuning these, especially the very first time you're starting from scratch, a general rule of thumb that I do, I either go one of 2 paths. When you're trying to tune stuff like this, you either multiply or divide by like a factor of 10, or sometimes I do by 2, multiply by 2, divide by 2. So starting at 1, dividing by 10, that was still too large, divided by 10 again, And now we're sort of in the ballpark. Ideally, we want this to lie right on top of this blue line. So it looks like it's a little bit too hot still. So yell out a number for me.
2.
I'm going to assume you mean 0.02. That would make it hotter, right? Yeah, now it's going even faster then. And as I imagine Logan's doing, you can be doing this on your own computer as well. So 0.009. That's a little bit hot for me still here. So I might go a little bit lower and see what 8 does. I like this better. And here's a situation where, like, is it better enough? Should we like maybe do 7, 9? You know, you could sit here all day and just tweak these until you get something that you finally like. Oftentimes what we do is, like, the very first time the shooter's done, we get it close enough. Like I might have been fine with that if it's the very first time we're running it, just so the mechanical people can see how it shoots a ball. But then eventually, when we have the time to sit down and really grind in, I would like to get it looking probably more like this. So we can see that it takes its sweet time getting there, but it finally gets a little bit short of the goal here. It hits a disturbance where the ball comes in, and then it's a little bit hot at the end there. But for the sake of brevity, let's call this good enough for right now. Now, another thing that's good to check is, does this work for other set points? So we're doing 300 RPM. Does it work for 600 RPM? Pretty good. Again, a little bit low here, maybe a little bit hot here, but that's perfectly cool. If it turns out that we need a short shot that's 300 and this long shot at 1200, it's deviating a little bit more now. But remember, this is without reading from the sensor at all. It's just using feed forward. So if we want to make it track a little bit better and deal with battery voltage a little bit better, what's the next thing that we should tune after KF?
P.
Yeah, P would be next. You would never have just a D controller. If it was just purely D, then your error would never change. So then the slope of your error would never change and it would have no effect. But Logan, you out here just ruin it for everybody else. So let's take a look at that again. So this is without reading the sensor at all. And then if we start adding P to it, now, boom, look how nicely it tracks. It got there super quick. It got there in, like, what's this, a quarter of a second? And then after the disturbance, it recovers super quick. So if it's a year where you're shooting multiple balls, like this year, or maybe a crazier year like the little wiffle ball year, you want it to recover fast too. So without that KP, it takes a little bit longer to recover to where you'd be ready to shoot again. So what happens if we make it bigger? So eventually, you see how the red line goes up a little bit here? That's what we call overshoot. I'll make it a little bit more obvious. So here's what happens when you overshoot. When your KP is too big for a perfect system at least, it'll overshoot, it will go over your goal, then come back down, likely under, and do a couple of waves before it settles out. If your KP is humongous, might not happen as much with a velocity controller, but it can be called critically underdamped. And that's when it just never recovers. If it was a chassis, it would just be doing this back and forth, never settling in on a goal. So sort of a rule of thumb is you tune it until it oscillates a little bit. You got this little overshoot here. I might even do a little bit more. If your control system can oscillate, if you're not worried about running into something, You get it a little bit higher than you want, and then you slowly back stuff off. So a little bit of oscillation, but we're getting to our goal very quickly, and we're staying at our goal very quickly, and we're recovering. So again, we could sit here all day and make this perfect, but that's probably okay for right now. What would we do next?
D.
And I would say it's optional to do this, but one thing, especially for a shooter, is adding D can help you recover faster. Because all of a sudden, your slope of error, this slope right here, is negative. So it's going to add a big extra oomph to help it recover faster. There's a Wikipedia page on how you should do this. And like, I think it's KD should be 1/10 when you start tuning and then go around from there. But probably not that, because that doesn't look good. I don't know. We won't spend too much time on that. But yeah, in general, you could sit here doing this all day, and it depends on how perfect your shot needs to be, how accurate you need to be, how quickly you want to recover. And I'll tell you, we did it pretty quick here, but it takes a lot longer in real life. This is a perfect system without any noise in it. You also don't have to worry about going and chasing your shot and putting it back in the robot, or having, a handler do that for you so you can shoot as many as once. It happens a lot faster when you can simulate it like this. But this look pretty decent. Did this sort of make sense?
I had one question. So when you're adjusting the KP value, it seemed the line seemed to be more flat at 0.1. Was there any reason why you switched it to 2.5 instead?
So it is flat, and then if we do this, it overshoots and eventually settles. Not necessarily. It looks like Logan's number actually does settle better at this 0.1. So there's a lot of eyeballing, and that's just, it's just eyeballing and guessing and checking and stuff.
Okay, just making sure there wasn't any specific reason to go a little higher.
Not necessarily. It in some cases it will help it get to your goal faster. And if you have a big swath that you have allowable error in, maybe you're okay with that little bit of oscillation, and you would prefer getting there fast with a little bit of error as opposed to getting there slower but with a very small error. Depends.
Okay.
It's very situationally dependent.
That makes sense.
But that's a good question. And yeah, let's take a look when it's under damped, as it's called now. So the slope of the line, it takes longer to settle to our goal, the smaller we make this number, right? So yeah. They give you a solution. Did you steal the number from the solution? No. Oh, we should also check, does it work for other RPMs? So you can see if we try to go 4 times faster, it takes a while to spin up, but it still gets to our goal. It holds steady on our line. What happens if we do this now? Nothing. I think this is too fast. It's probably saturating the controller. So there it's like 2.2. Yeah, 0.1 seems really good. So ignore me changing that. Cool. So in general, velocity controllers are easier to tune than position controllers because your KF is taking up most of the work here. Now, my mortal enemy, if we want to do this one. Link out. So this is a arm that looks like it can go 360 degrees around. So this is the situation where we have to fight gravity, and we have to do our cosine math if we were writing the code. Luckily here, it's just the knobs. So what should we do first? Oh, and what kind of controller is this? Is this position or velocity?
position.
Yep. So what should we tune first, given that this is a position controller with nonlinearity? I should have told you there's a solution.
I'm gonna guess P.
Okay, so let's try that first. So shout out a number that we should start with. It's something to think about. Your numbers sort of have a physical meaning. So if you are tuning something in degrees, it's like a ratio of degrees that you're doing. This is doing it in radians, so it's going to be, not quite 180 times smaller, but there is some connection to the physical world with these numbers.
Let's just go with 1, I guess.
1. So there's oscillation. I don't know what it should be with these units. So it's trying to get there. It's fighting. I think we got to keep going bigger.
Yeah, I just tried 10. Maybe
it's getting
15.
closer. Eventually settling out. I would be very stressed out if my robot did this on the field. Probably be very hard to drive too.
They're waving at you, that's all.
So what do we think's happening? If we look at the control that we're giving it, our actual measured thing, why is this tough?
Most likely because it's not counting for gravity right now.
Yeah, so like right here, it's getting close. So then our output power based on P is getting smaller, but then eventually gravity takes over and yanks it down back to Earth. So then we're like down here, oh no, I got to put more P in. My air is big, my P component's going to be bigger. But then as you get close, gravity takes effect and it's going to just oscillate like this forever. So what should we probably actually tune first, given that this is nonlinear?
kg or the gravity.
Yep. Yeah, so under the hood, this is some constant that's multiplied by the cosine of your current angle. So let's just try a number out. So what we would hope to see is when we tune this perfectly, this arm will just stay at wherever it is at time 0, which I think is probably like 45, 90 degrees, I guess. So it's not holding itself. So what should we do to the number? Bigger, smaller? I'll give you a hint. It's not keep it the same.
Bigger.
Okay. You got a number in mind? Since I'm sure you're doing this on your computer.
Well, whenever I had KP, it's good at like 6.27, but I removed KP and it looks great.
Okay, so here's what's happening at 6. So what's happening now? And what should I do to my value based on the behavior that we're seeing?
I would lower the number.
Yeah, so our goal here is to have it be staying the same, not moving up and not moving down. So right now we're giving it too much power. We're overcompensating too much, so it's going up. So let's try 5 because that looked close. Okay, so that is clearly not enough. 6 was too much. We can let's try splitting the difference here, see what that does. So that's not enough. Let's split the difference again. We're closer. It's falling slower. Falling even slower. We'll raise it a little bit. Okay, so 6 was too much. 5.9 is close, but not enough. So now we can start going to the next decimal place over. All right, somebody tell me what I should do now. Shout out a number at me.
5.93.
9.3. Ooh, that looks is going up a little bit. So I'm gonna do 2.9. Still a tiny bit.
0.925 is really smooth.
Yeah, that looks pretty legit. So now we are making our system linear again, right? We're canceling out the effect of gravity. So now what should I do?
Now we adjust KP.
Mm-hmm. Try year 1 again. Can't really see what's going on. Did I like zoom in on this or something? Let me refresh the page. Or let me give it a different goal, I guess. Okay. So I guess here we go. We'll make it go almost vertical. Okay, so what's happening now with my KP of 1? What would we call this based on the terms I was using before?
Oscillation?
Mm-hmm. It is oscillating. It is overshooting as well. Same idea. To oscillate, you kind of have to overshoot. Okay, so based on that, what should I do next? Let's say that we're still focusing only on KP. Let's say we were trying to reduce oscillation. What would I do to reduce oscillation? Lower KP. I like that. That barely did anything. So now if I do that, it's overshooting once as opposed to here it kind of overshoots and then undershoots. It oscillates like 2 cycles. If I do this, it dips down a little bit, but it's more like one thing instead of up and down. So that's good, but here it takes 5 seconds, I guess 4 because it starts at 1. It takes 4 seconds to get steady. So this is a situation where you would probably want to start doing D because that's longer than I would like it to be. So usually when you're adding D, you can make it oscillate with like a reasonable amount of intensity. Like that's legit. And now if I add D to this, it should smooth out these oscillations. So you see how that did that? Oh, look at that. So by adding my break to the system, it's kind of canceling out that oscillation. And now I get to my goal in 1 second instead of 5. So again, we could play around with these numbers all day. Let's try a different set point, see what it does. So it looks pretty legit. If we're happy, if we're okay with overshooting here, like this would certainly be good enough for me to start doing driver practice in the middle of the season, right? Maybe I would want to tune this a little bit more, but this is like a not bad starting point to go to. Cool. Does anybody have any questions on that? Now, this one is super annoying to tune in real life because you got to get it to your position and then try tuning it. I swear, everybody thought that we were going crazy the day that we tuned our intake. They just kept coming over. We were just doing this for like 2 hours straight. Zzz, 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 zzz. And it was just super annoying. It took a ton of time. But does anybody have questions? Does everybody understand why we added our gravity to offset the nonlinearity and all that stuff? Good, good, good. So yeah, anytime you have a nonlinearity, the two I'll try to give an example in a second. Yeah, the two big ones would be an arm such as this or an elevator that you have to account for. One other situation is if you have a skid steer, a tank drive, it takes a lot of energy to start a turn. But once you get going, once you break your static friction, you spin like a top. It's super easy. So you can do a similar thing there where you can find out what voltage it takes to actually make it start turning. If you've ever driven a tank drive with low battery, you can like it digs into the carpet and really, really doesn't want to start moving. So that would be another situation where you might want to add an offset to your PID controller. So if you were writing, did I share just Chrome or can you see IntelliJ right now? IntelliJ, cool. So if you're going to write one of these by hand, you would have like double KP equals whatever. Right, so the normal equation for a standard P controller would be output equals error times KP. Super easy, right? And your error being my goal minus current, right? So super easy. That's why P controllers are nice. It's a one-line thing, right? If you were adding derivative means that you have to look at your last thing too. So you would have like a last error outside of here. And you would do last error minus error times KD. So now we have a PD controller. And if I needed feed forward, if I was doing a velocity thing, hold on, I'll do. P controller, PD controller, and I'll do a PF. That's the most common one that we would do. Our feed forward, so we're not going to look at error for our feed forward component, right? It's just going to be our goal, so like 1500 RPM times KFF, or KF, the two different vendors use them differently. And then on top of that, we can add our P component. Now, a super handy thing is that we don't actually have to write this. WPI provides a PID controller. Rev and CTRE provide PID controllers that you can run on the speed controller itself. And the nice thing about that is imagine the robot was super slow and you only measured stuff every second. Normally the robot runs 50 times a second, aka 20 milliseconds, but imagine it was a second. You know, you can travel a lot more time in that second. And because of that, it's harder to make corrections. You want a really tight loop. You want to have you do the checks as frequently as possible. So the nice thing about running them on the speed controller is that it runs 20 times faster, 50 times faster than it would if you ran it on the RoboRio, which is handy, and it's less code than using WPI's thing. But regardless, so this stuff is all handled by that, right? You give it a goal, you give it your current, and it spits out this number. So how would you add compensation for stuff? So so we'll have some magic PID controller that's either the WPI Spark or Falcon thing do its witchcraft. And then basically for an elevator, we always want to add the offset, right? It doesn't matter if we're going up or down. It doesn't matter if we're halfway up or whatever. As long as it's a vertical elevator, gravity is affecting it the same always, right? So we can just add gravity offset. And I'll say, right? So, well, this is how you would do it with the WPI PID controller. They would give you a base value, and then you would add gravity offset to it. If you were doing one of the speed controllers that has it built in, it looks a little bit different, but there's a way that you can add arbitrary stuff to it. So here is actually an example in this code lab of it doing it for the elevator. So here's how you do the magic under the hood stuff for sparks, for rev. So you say, here's where I want to go. It already knows where you are because the encoder is mounted in the motor. And you say, I want to arbitrarily add this percentage output to it. So you would go tune your KV or KG or whatever and add it like this. Now, if it was a super annoying arm, it would look more like this. Coder decket angle, right? Whatever. And then our arbitrary offset would be math.cosine of the current angle. And then we would put that number in here instead of our constant gravity offset thing. Does that sort of make sense? Where did I do that, Ava? I very much might not have needed to. Was it in this first chunk? Oh, this? Oh, I'm saying, so if this was an object, so theoretically, I'll type the full thing out to be explicit. Here's WPI's PID controller. The actual thing I would do is PID controller dot calculate, I guess. So I was shorthand cheating. This is more what it would look like in real life. Does that make sense? Does that answer your question, Logan? How to add this stuff in? Do you have something else, Ava? Yeah. Sorry. Yeah, there we go. So again, this is all hypothetical, me typing fast, but theoretically, most likely, you would have a constant in the class. I'll even put it in the right spot-ish here. So this would be like private static, final, double, you know, whatever it was before 0.1 or whatever. So this is a normal variable, right? So I don't need any parentheses to talk to my normal variable, but this is an object. So I got to call the function inside of the object to get the base stuff going. The semantics are the hardest thing to learn when you're first learning a programming language. Why do I need parentheses here? Why do I need a semicolon here and not here? Does it all sort of make sense? Theoretically, at least. I'm gonna blow it away. Boop. Okay. So that is PID control. You can spend a lot more time talking about it, doing a lot more examples. Another one of our programming mentors, Joe, made a more in-depth deep dive into it that I would be happy to talk about at another time. But for the sake of moving through the rest of the topics I want to go through tonight, we will continue on. So I basically talked about that. So another way that you can control, so PID was like the thing in FRC for a long time. And then the cheesy poots came along and were like, hey, trapezoidal motion profiling's existed for a long time. Let's start using that for our things. So the basic idea, again, there's a slight calculus tie in here because there's a beautiful relationship between acceleration, velocity, and position. So it uses a little bit of that under the hood, but really just to the point that it generates a graph that looks like this, sort of. So here in red, we have acceleration, in black is our velocity, and then blue is how that all transforms into a position. So imagine you're in a car. If you have your license, you could be the one driving a car. And you're driving down the road. And it's a lazy Sunday, you're going to your friend's house. So you're on a bunch of side streets, you're going from stop sign to stop sign. You can casually step on the gas, cruise along at the speed limit, and then casually step on the brake and come to a stop at the stop sign, and just keep doing that through all the blocks. Now, if you're running late for school, you shouldn't do this because you're all dumb children, but maybe you step on the gas a little bit faster and get to that speed limit, stop sign faster. So that would change the slope of this line here, right? You're increasing the amount of acceleration, you're getting to the speed limit faster. And then similarly, when you get to the next stop sign, you're hitting the brakes a little bit harder than you did before. Or maybe you are driving in snow and ice, and you want to be even more gentle than you were on your Sunday drive. So the slope of this line would decrease, and maybe it's so slippery out that you don't even get to the speed limit. So rather than looking like a trapezoid, it looks like a triangle. But the idea there is that you have control about how fast you get to the speed limit, right? So that's the first third of this chart. Now, once you get to the speed limit, you're not accelerating anymore. You can put your cruise control on and just cruise at your cruising velocity. If you're driving around side streets, that might be 25, 30, 35, whatever the speed limit is. When you get on the highway, you're going to be doing the same thing, right? I get on the on-ramp, I accelerate for a period of time, then I cruise along at 55, 65, whatever the speed limit is. And then once I get off the highway, I decelerate. So you're always kind of following this path. And if you ever notice yourself walking, you're probably doing the same thing. There's a period of acceleration, a period of cruising, and then a period of deceleration. So the very cool thing about this is, bye, Sarah. The very cool thing about this is if we have a position goal in mind and we have some sort of max acceleration and max velocity that we feel comfortable with, we can work backwards and make these charts. And the very nice thing about pre-planning a path is that if you remember from before, we tuned the shooter way quicker than we did the arm. Because as I mentioned, velocity is way easier to tune. So even though we have a position goal, we can translate it into something that we can control the velocity over and have it still go to the right position. And that way it's way easier to tune because KFF is our best friend if we can ever use it. And another super helpful feature about this is, let's say we wanted to make that arm thing go faster. How do we make it faster? We raise KP. Well, if we raise KP too much, it's going to oscillate. But with a motion profile, you can start out saying, I'm only going to go 5 feet per second. Okay, I need to trim time off. I'll raise my speed limit to 6, 7, 8. And it all kind of magically works if you tuned your controller well. And you can do the same thing with acceleration, right? I don't want to spend all this time speeding up. I'll stiffen these lines up on the end. And it just makes it way easier. So whenever possible, I recommend that you try to use trapezoidal motion profiling. Again, WPI provides a library for it. SCRA provides a library. I believe they call it SMART. They call it Motion Magic. And Rev provides a library for it, which they call Motion Magic. Smart Motion, whatever. They call them different things. But the same idea is under the hood is all the same. It's a trapezoidal motion profile. So that's like kind of the classroom portion I wanted to talk about. So before we jump into the code lab and I have you guys clone the repository, How do you think we would go about tuning this? What steps do you think we would go through? So is this a position or a velocity controller? A trapezoidal motion profile. Two different answers, and it's confusing to think about. It's a position goal with a velocity controller. It also does like some fudging around the position, but we can think of it for most intents and purposes as a velocity controller. So given that it's a velocity controller, what should be the first thing that we would want to tune? Yeah, so usually I try to make a nice long flat trapezoid like we have here, and I try to get my velocity touching the top of that trapezoid as good as possible. And we do that by tuning our KF. And then you can go through and deal with the noise a little bit by adding P, but velocity controller, KFF, best friend. Is there any questions on that? This is also something that you could talk about. We could talk about how you generate this and the calculus behind it, how to calculate the slopes and do the integration to see how much time you need to accelerate for. But I like to kind of leave it at the high level. Understand what it's doing, but you don't need to know the guts of it right now. I encourage you to take a look at like Cheesy Poofs. They did a whole thing in Championship a couple years ago about how you can generate these things. All right, if there's no questions, how about we take like a 10-minute break? So like 6:40. And during that break, boot up your IDEs and we can test your what you learned last time, even though we didn't really teach Git. Let's see if you guys can figure out how to clone this repository. Don't feel bad if you can't, because we did not do a full Git tutorial yet, but we're going to be working out of this repository, tuning knobs on a robot. So I'll stop the recording. I'll hang around if anybody has questions that they want to ask when the recording's off. But we'll meet back up officially at, oh, I read my clock wrong, 6:50, let's say. Get some water. Stop share. And it's a smaller group than last time. So, and also just so we have it recorded, I don't think we'll do breakout rooms. So we can, if one of you guys wants to take the lead and do the screen sharing and the tweaking of the numbers yourself, I'm more than happy to let you do that. Yeah. And Anuva, if you want to do it, if you have Eclipse open, let's just take a second. Let's see what that looks like if you share your screen with Eclipse open. I haven't used Eclipse in a while. I'll have to remember how to do all these things.
I don't know how to make a clone of it though, so I don't have like the files in Eclipse.
Yeah, if you have Eclipse open, can you just share your screen? I'll try to do it from 5-year-old memory, how to clone it. Okay. Oh God, it's been a while. You might need to install Git too. If you have to install Git, it's not worth it. Try
installed. I should already have Git.
Oh, you do?
I'm pretty sure.
Let's try to do it from Eclipse first. Can you try maybe clicking on source on the toolbar? I kind of doubt that's it. Yep, no. What about file? What's under file? New? Oh, I think, hold on. Go back to file and then go down to import. Yeah, Git. Projects from Git. Clone URI. Yes, perfect. Perfect, perfect. Next. Next. wherever you want to put it on your computer. I like that place. That looks good to me. So you can hit next again. Yeah. It's not an existing Eclipse project. Go back. Try general project maybe. I don't know if you have to have a plugin for yeah, hit finish. I don't know if you have to have a plugin for Gradle or not. Does Eclipse have a terminal?
You mean a console? I'm not sure what terminal is.
Can you type in that console? I think that's just for output.
Yeah, console is just output. I can.
Well, you certainly have a terminal on your computer somewhere. Are you on Windows?
Is this terminal that you're talking about?
Oh yeah, let's see what that does.
Still can't type in it.
Are you on Windows?
Yeah, I am on Windows.
Can you do Windows key R and then type CMD and hit enter?
Oh, just command prompt?
Yeah.
Okay. Yeah.
If you know your way around that, if you can CD to the CodeLab directory.
Ooh, I
Okay,
know how to do it, I just don't remember where we saved it.
I think it was in your user directory /git/PID CodeLab.
Okay. All right. I'm just gonna see if I can get the file path, and then hopefully that'll help. It's in a folder called Git, right?
I think it was your user directory /git/PID CodeLab. Yep.
Right.
Well, anyway, if you eventually CD there, try doing this. In the meantime, I'm gonna share my screen. All right, you see my IntelliJ? Oh, where'd the chat go? I lost everybody's video. I don't know if you're doing the thumbs up, but I assume you see my IntelliJ. Okay, so the robot project is very similar to what we did on Monday. It's just got a couple more bells and whistles in it. So it has a chassis subsystem that we're going to write PID for or tune PID for, an elevator with PID, a punch, and now it has a shooter, so we can do some velocity stuff here. The commands should be pretty much the same as what we had the other day, except this actually has the code written for it. This is like a completed version of the code lab. But then I also like to have a couple of extra commands when I'm doing PID tuning, or like finding out what goal I want, what RPM I want to shoot at this distance, and so on. So I personally like to break them down into folders. So here's our normal commands, and here's the one specifically for tuning. So feel free to look at those. We'll be running these commands from the simulator. And similarly, I like to break autonomous ones. These are only used in autonomous. So different ways to drive a distance, drive a fancy trajectory, and initialize our pose on the field. And then a place to create autonomous modes and all that sort of stuff. But anyway, so the structure should look familiar, and the code in here should look pretty familiar to what you guys did the other day. I think that both groups got through all the teleop stuff, like driving the elevator with the joystick and the chassis with the joystick. It looked like one group had done the timed autonomous thing, and the other group was doing the not timed autonomous driving thing. So there's a little bit extra code in here, but that you haven't written or seen yet, but feel free to take a look. But we'll dive into running the simulator, which I didn't really talk much about at the last meeting. Super duper handy. Give you a tour of that and some of the nice features that come along with that if you're doing command-based stuff. and then we can get cracking on tuning. So if you are using IntelliJ, as I am, there should be up here, I think I actually committed this time, so there should be a simulate run configuration. So you can select that, hit the big go button. If you're on VS Code, there should be a W sort of on the top right here. And I believe if you click that, there will also be a simulate button. I think when you run it from VS Code, there'll be that a little prompt that comes up in the middle if you want to simulate with the GUI or not. You absolutely want to simulate with the GUI. So what's popped up here is you have a question, Ava?
How do you get the simulation to run on VS?
Give me a minute. I think also another option is if you do Control-Shift-P and type simulate, I think it will come up with an option. Well, let's see.
Do you want me to screen share?
Sure, that'd be easier than me opening it. This is the wrong project I got. I will stop. Yeah, go for it. Oh, weird. Where's the WPI thing? Yeah, let's go with the Control-Shift-P option, I guess. Let's see if that. Did you already have VS Code installed and then also did the WPI version on Monday, or did you?
Oh, yeah, I forgot about that.
Okay, yeah. So for whatever reason, they have to ship some proprietary version of VS Code. So if you open that up, then you should have the simulation options. Yeah. For the people using, oh yeah, I can share this. So I currently am not, this isn't a robot project. This is the docs, but up here, if you open the VS Code version, you should see this W up here. And then if you click on that, it comes up with all the WPI libs and you should see simulate robot code. Java, I don't know if that one would come up for you. And then your prompt will look different because you have an actual robot instead of documentation. But that's how you would do it. Anyway, so this is the simulator, super duper handy. So you should see something more or less like this. I have already added a bunch of things to it so that we can go through and look at fancy charts once we're start tuning stuff. Woo. Also a side note, this robot is like impossible. I made it drive like 50 feet per second. I just made it a real monster to tune. So this thing just flies across the field and is impossible to control. But anyway, so this is the simulator. It's also referred to as the HalSim GUI, GUI being a visual thing that you can look at. And yeah, so it's built on top of another thing that WPI built called Glass. So that's a tool that's installed that could be used as another dashboard. If you like the way that this plots stuff and you interact with it, you can use that as your, dashboard on the driver station if you want. But this is a slight layer on top of it that allows us to run simulations. So over here, let me pull the chat up so I don't miss anything. There is no camera support at the moment, no. So you wouldn't want it to, it's very helpful for programmers, not so much for drivers. So if you were debugging and you wanted to reuse your plots, you could use it as a dashboard in that effect, but not to actually drive the robot if you want a camera feed. So yeah, take a tour. So up here on the top left, just like you have on the driver station, You got your enable, disable, autonomous stuff. By default, just as in real life, it starts disabled. So if you want to play around, make sure you hit the enabled button up here. You can do cool stuff like you can pause the robot if you wanted to look at plots or do whatever, do some debugging. You can actually pause the simulation, which is nice. You can configure joysticks over here. So I believe that I should have already done that for you so that you can drive the robot around with WASD. It's very hard to control. And then you can also move the elevator with I and K. So you can hook up joysticks. You can use a keyboard like we currently are, or if you had an Xbox controller at your house, you could plug an Xbox controller in and then drag it over to whatever joystick that you want. I'm going to close those because we don't really need them. And we can also see like what stuff is plugged into the robot. So we have 2 limit switches here. I didn't name these, but you can like rename anything you want. Swith. We have our special motor controllers over here, along with our gyro and our compressor. If you have LEDs, you can look at them on here. Just it gives you a tremendous amount of insight into your robot. You can add plots, as I've done here. You can collapse stuff, as I've done here. Down here is a part that we're going to be playing around with a lot tonight. So I haven't mentioned this before, but there's this magical thing that WPI gives us called network tables. And basically, it's a way for the robot to communicate with something else through like a cloud, you could think of it. So one thing that you might have used already is a Limelight. The Limelight publishes data into the network table, and then your robot reads from the network table. Similarly, your robot can publish debug information to your dashboard, your smart dashboard, shuffleboard, glass, whatever. You can publish stuff to it. You can tweak constants and have the robot read them back, which is what we're going to be doing heavily today. So we'll be changing stuff on the network table through this interface. And now one thing that's super cool about the command-based framework is that you can actually display a command as a button that you can run. So I put them all on a shuffleboard tab, command tester. If you go to network table, shuffleboard, command tester, here's all the commands that we have implemented and that we can run. So the thing that I want to start out with down here is tuning shooter FF. So I'm going to add that. And now I got a button here that I can run the command. I can cancel the command. Cool stuff. And like I said, this also works on shuffleboard. Since I probably haven't shown shuffleboard before, why don't I launch that? Even though it's going to destroy my computer. So yeah. I've got all these plots here. So the very first thing we want to do, just like we did on WPI's website, I want to tune our shooter. Now, the easiest way to calculate FF is to give your motor some voltage and see how fast it spins. How fast does it spin when you give it 6 volts? How fast does it spin when you give it 8 volts? And then from that, we can invert our equation and get KFF. So all this command does, if we go and we look at it, tune FF gain. All it does is it takes a number from the network tables, takes some speed, and it drives the motor at that speed. Shuffleboard about to wreck my computer. It drives the motor at that speed. So it gives it a percentage of voltage and just sets it. So raw, no control, anything like that. So side note, here's shuffleboard. This is what we use for our dashboard, something WPI provides us with. You can have programmatically added tabs. So here's another view of all the commands we can run. We can similarly hit it, run it, yada, yada. It'll also, there's a special network table called Smart Dashboard. If you publish stuff to that, it'll automatically get put on this page. So we can see like how far the write encoder has gone, what motor percentage it is, all this sort of stuff. You can put combo boxes down if you have autonomous modes, which apparently I didn't write any, so there's nothing in the combo box. And over here is how Shuffleboard represents the network table. So it's the same thing as the Halcyon GUI is doing here, just represented different. So I can go and I can just drag something over to here. Also, anything that's a number, you can right click on it and you can show it as a graph. You can show it as a number bar, a dial. There's all these sort of different ways that you can visualize this data. So long story short, Shuffleboard's super handy. And Shuffleboard can display camera feeds. So if I had a camera hooked up, it would show up here like Limelight, whatever. I can drag my Limelight over here and now I got a camera feed. It's very resource heavy, so I'm going to shut it down. You can save your settings so it persists to the next time around. But we're going to stick with glass. Yeah. Okay, so where's my shooter plot? Here it is. So right now, if we look at our preferences here, preferences are a feature that WPI gives us where we can set a number and it will actually write it to the robot's hard drive. That way, if the robot turns off, it'll get saved on its storage. And the next time we boot up, we can read that number, whatever it was the last time that we saved it. So Girls of Steel, actually my previous team wrote a little library around it. So it's a little bit easier to interact with. But basically, we're just talking to the preferences network table. So here's all the preferences. So right now, if we run this command, it's going to set a very small speed, very small. I'm going to actually make that 1. So right now, because I did that, our shooter motor is going full speed. You can see this little plot here. Cool, cool. We can watch it go up over time. It's starting to settle down. So if I go and I look at the shooter's velocity, it's hanging out right here. So if I'm giving it 1 power and I'm going 4,700 RPM, how can I calculate what my FF should be? What's the relationship between those 3 variables? Anybody? Here, I'll write the equation out again. Give you a hint. Made it not so obvious. But so I'm going, when I give it a 1, when my output is 1, it is going 4,700 RPM. So how could I calculate KFF? The battery is probably at 12 volts. You don't really need to take that into play. Because this is going to give us a percent output, so the -1 to 1 thing. So that doesn't take battery voltage into account. But regardless of the battery voltage, it should get us pretty close. Here, I'll make it a little bit easier. I'll get rid of the distraction. So at an output of 1, my RPM is 4,700. Yeah, we're trying to solve for a KFF though. So I want like KF equals rearrange the equation so it's KF equals something. Output over goal looks correct. So if we were to do that, that's 1 over 4,700. Boom, this is probably a pretty good KFF. Now, if you wanted to be fancy, you could also do this for different values. So like rather than bumping out at full speed, let's do half speed, see what it settles out to. In the meantime, I'm going to update my shooters KFF. Oh, I've got the working code lab, not the ones that you guys have. So a lot of these will be 0 for you guys. Don't cheat and look at my numbers. So that number that I had, you can paste that into here. And a weird thing about glass, you can't just type it and bounce away. You actually have to hit enter, physically hit enter. Okay, so now that I'm going at 0.5, I'm getting this velocity. So let's see how they compare. So that would be 0.5 over current RPM. Pretty close. So 3 significant digits. It gets the 212. One of them says 4, one of them says 7, but that gets us close enough. We'll call that a good KFF. I'm actually going to close this and check out the main branch so that I don't have the answers. So now that we have that, we should get pretty close to whatever goal RPM we set. So the next thing that I want to do to validate this is I'm going to run this tuning.shooter RPM command. So similarly, we have a preference in here that I want to go 1500 RPM. Right? And we can see this yellow line is our goal RPM. And because I got rid of my KFF, nothing's happening. But theoretically, if I put this in here, I should get pretty close. My 2 lines should coalesce. And that looks pretty good. Ridiculously slow, but it gets to my 1500 nonetheless. Let's see if it can do 1000. Gradually slowing down. Okay, so that's the recommended way that I tune F in real life to at least get a base point for it. If you have the ability to run your thing at full speed and do this reverse math, for some things it's harder. For a chassis, you might not have enough time to let it get up to speed, and you got to do it sort of the way that we did on the online thing. But anyway, so our F looks pretty good. What do I do next? KP. All right, shout numbers out at me. .5. Let's see what you do. I apparently don't stop the motor when that command stops. That's bad practice. So let's add 1500 and 2000. So let's try to go to 2000. So I think I forget how you zoom in on this. There we go. So what's happening here?
It's overshooting.
Yep. It's overshooting and it's oscillating. So we might be okay with that because, like, what is it? It's oscillating by 20 RPM, it looks like. Or it's like plus 20 minus 40, it's oscillating between. So that's a situation, like, depending on how accurate your shot needs to be, maybe it doesn't matter. If you wanted to shoot into the low goal this year, it was easier, and you could probably have a lot more error than if you're trying to, you know, not make it bounce out of the angled high goal, right? I'm guessing you've already done that. let's see what it looks like if I lower it. So less oscillation, as you would expect. Let's also, I'm going to zoom back out. Let's just quickly time. Let it slow down. This is more realistic where you got to like wait for things to slow down. So with no KP, if I do it, it's looking like it takes, geez. I made all of these motors like absolutely ludicrous, never have in real life. So that takes about 7 seconds with no KP. If we do, you said 0.5. We'll let that dude slow down, go back to 0. With our KP, we get there in about a second, which is pretty good. And if we zoom in, we got that oscillation. So let's try. I did not make it easy to add D, so we're just not going to do that. I didn't make a preference for it. It's not hooked into the back end stuff. Just K, just PF controller. That was lazy of me. I apologize. But so again, we could tweak around with this and try to make it oscillate less. It's kind of the way that it's oscillating makes me think that our F might not be high enough. Or too high or something, the way that it's going. And it's a little bit hot. But right now, we'll call that good enough. We can quickly oscillate quickly go between our close shot and our far shot. It gets up to speed super quick. I don't have a way to simulate a disturbance like they did when the ball hit the wheel, but yeah, feel free to play around with that more on your own time. I can also show you how to add D with our properties. It's not hard. I just don't feel like doing it right now. I'd rather keep checking. Okay, so that's the shooter wheel. Again, velocity, nice and easy. So now let's, yep, I can do that. Let's go to, let's tune our elevator. So this is a linear elevator, goes up and down. What's the first thing we want to do here? My opinion didn't change. You can start yelling stuff out. Oh, I should say, well, no, you're not right. We are going to be using trapezoidal motion profiling for this. But regardless of the control mechanism, this is an elevator, right? What's special about an elevator compared to a shooter wheel?
Gravity.
Gravity, yep. So luckily, I made a tuning.gravity compensation command. So similarly, yeah, I would prefer if you yell stuff out than me waiting on the chat. Elevator compensation. So similarly, we're just going to be setting a raw speed here. So we'll tell the elevator to use the same thing we would do with a joystick, and we're setting the motor speed. And we want to find what % output it takes before the elevator holds its own weight. So if we run this guy, we'll just be setting a raw speed. I've got velocity down on this bottom chart. So I want to tune this elevator gravity compensation speed. So what should I do? We're just adding this as a % output, so value between -1 and 1. It's probably going to be positive. So like, how much power do you think it's going to take to hold this ridiculous elevator up?
Try 0.1.
Moving on up. So what should I do based on that? Was that too high, too low, or Goldilocks? Come on.
Is the little blue line on the lower graph, the velocity graph, is that the target?
That is our speed limit for motion profiling. So right now, I stopped the command, so it's not running. There will be, if I ran it again, the orange line on the bottom is the velocity, and the orange line on the top plot is position. So it's raising itself up with
Okay.
this offset or compensation factor. So does that mean that it's too big, too small, or just right? Nobody knows? You know, Tim?
The value's too high.
Yep. It's too high, right? We want this to stay still. We want to find the threshold where it just barely doesn't move. So I'm going to cut it in half. Okay. It doesn't look like it's moving with that. We can verify by looking at the
Is
velocity
the
right
command
here.
running?
It is not running, so that would help. Thank you. So, but still, the point remains that it is not doing anything, it would appear. So let's split the difference between them. We'll binary search our way to this. Okay, so point, now what's going on? Same thing as before, right? It's too big. So I'll try 0.6, kind of just guessing and checking. I'm seeing that there's still no velocity coming out. Let's blindly try 6.5. Still nothing. And the command is running. 6.7. Still nothing. Oh, that didn't take. It looked like 6.7. Nothing. Wasn't 7 too high? Oh, 7. Wait, 7.5 was too high, right? Yeah. 7.1's a little bit too high. Let's do 7.05. That's got this tiny bit of velocity here. This is something that, you know, in real life is real hard to get perfect. So as long as you're canceling it out pretty good, if it's got a slight bias to go up or a slight bias to go down, you just got to kind of figure out if you're okay dealing with that or not. 0 made it. Well, that's probably why. But we could spend all day on this. I'm probably fine calling that close enough. It's holding its own. It's a little bit up in the air, but if we put it back down to the ground, it's going to go up ever so slowly, but I'm going to say that's okay. Okay, we're compensating for gravity now. And we're doing so now it's a linear system, and we can do normal PID on it and normal trapezoidal motion profiling on it. We are doing trapezoidal motion profiling. So the first things that we need to set with that, we have our speed limit. Oh, I didn't mention this before. WPI provides all these simulation libraries and like complex math and physics solvers and things. And they all expect you to be using meters. So I highly recommend that you do the same. It makes your life a lot easier if you live in meters and then occasionally convert to inches like we're doing here. But like have the motor controller speak in meters and all the other SI units, meters per second instead of inches per second or feet per second. It makes everything a lot easier. So here we're saying we'll go 0.1. Our speed limit is 0.1 meters per second. Which is outrageously small. Let's say 1 foot. Oh wait, no, this is an elevator, not a drivetrain. So maybe that's okay. We'll have it go slow at first. So that's our speed limit. And then similarly, we're saying 1 meter per second for our acceleration. So it should be, that means that it will take 1 second for the elevator to get to full speed, which is very slow. You wouldn't want to run that in a match probably, but for the sake of tuning right now, it's usually good to start slow and build yourself up. So if I have a trapezoidal motion profile, what would be the first thing that I tune now that I have a speed limit set up?
No, would it be acceleration or no?
So these two numbers here, acceleration and velocity, are constraints. They're not really something that you tune. You could tune it to make it faster if you wanted to, but they're like parameters that are set up to generate the shape of the thing. Once we have the shape of the thing, we want to be tuning. It's a velocity controller at that point. We want to follow velocity. So if it's a velocity controller, what do we tune first?
Speed forward.
So I'm going to add, I believe that I have a lift to high, lift to low. I'll put these guys over here. And a lift to middle. Okay. So if I run this without setting anything, as we would expect, it stays mostly still, except for a little bit of gravity drift. So yeah, let's do this. This is a situation where it might be harder to do the run at full speed and do that equation we did before because your elevator has a limited range. You can do it. You can jam your joystick forward for a little bit, take note of what the max speed was. But let's do it the old-fashioned way just to get practice doing it both ways. So let's say that we do 0.1. If I try to go high, of course I would pick a value that's perfect. So let's say it was 1. Let's do it again. What? Yeah, so 1, if we look at the velocity thing, we want to have a nice looking trapezoid that has a top like that. So 1 was too high, but apparently the number that I pulled out of my hat of 0.1, see you, Nuba. The number that I randomly pulled out of my hat before, it was a, oh, well, what happened? It was pretty good. So it's a little bit hot, I suppose. But that's probably good enough for right now. So if we look at this, there's our nice trapezoid shape, right? It's doing the trapezoid motion profile. It's doing it super slow, but we're eventually getting there. I can't zoom out in that way. And there's our deceleration side. So that looked pretty good before we started adding P in even. Like it overshot a little bit. Our gravity compensation probably doesn't help with that. But let's raise our speed limit, I think, because this is going painfully slow. So let's make it go like, oh, that's acceleration. Let's say that we want to make it go 5 times faster. So now we expect our trapezoid to hit up here. So let's let it come back down to Earth. If we run it now, if we tuned our KFF well enough, does anybody know what happened there?
It got to some point before it hit its maximum speed.
Yeah, exactly. So triangle motion profiling is the same sort of idea. Yeah, so let's raise our acceleration up too. Yeah, remember the correlation between these two, right? Like acceleration is meters per second. So if I wanted to get there in half, if I wanted to get to the speed limit in half a second, what should my max acceleration be? So if my max velocity is this, let's say that I wanted it to take a second to get to the max velocity, and my max velocity was 0.5. What should my acceleration be for me to get there in 1 second?
0.5 as well.
Mm-hmm. Yeah. This is usually how I do this stuff. Like I have them be equal for a while. Maybe I double it. So if I wanted it to get there in half a second, I can make this 1. But let's do this 1 second thing. See if we get a nice trapezoid out of it again. We hit our speed limit, nice trapezoid. We're at our set point, nice and perfect. This is looking good. Let's get this down to earth. Works for the middle position as well. So remember, we're only using KFF right now. We're not even looking at the encoder, but we tuned it so dope that it's like doing exactly what we want. Now, if the battery went down, it would have trouble, but that's where P comes in. So we can add a little bit of P here. We'll just blindly pick 0.1 for this too. Let's see what happens there. So what happened if we look at the velocity? Remember, we're doing a velocity controller. So we kind of want to be looking at this plot. What happened?
It overshot.
Mm-hmm. That's exactly right. So this is probably a little bit too high. Let's just cut it in half, see what that does. We could have done it by 1/10 too. That would have and worked our way based on that knowledge. So it overshot a little bit. Looked a little bit better, maybe. Cut it in half again. So it overshot a little bit, and you can kind of see it did a little. Not quite oscillation, but it did a little something. How do I reset this? Well, it's just going to be like this forever now. But yeah, if we were doing just a P controller or a PD controller, it would take us a lot longer to get to a nice result like this. And like I mentioned before, if we want to increase the speed limit, like it's super easy to do. This elevator really has some punch, so I think we can probably make it like, it's not even on the chart anymore. Let's see if this works. Let's let it fall down to earth. So that's like 1.5 seconds to get to the top, to get 38 inches in the air, something like that, whatever this is. So way easier to adjust your speed and your path to get there if you're using motion profiling. Is that sort of making sense? Cool. And one thing that I can't recommend enough is like, this would be much harder to do if we were just looking at numbers, if we were just system.out.print lining stuff, right? So I highly recommend, whether you do it in shuffleboard or in glass or whatever, have some way of visualizing your data like this, because it's much easier to see what's going on. and having as many debugging hooks, like these debugging commands and these tuning commands. Write them early and write them often, because you'll never know when you need to come back to them. You don't want it to be like a one-off thing. We have our tuning commands checked in all season, ready to retune something at a moment's notice. Cool. Yeah. So always be on the lookout for this nice, beautiful trapezoid or triangle shape. Makes things a lot easier. Now I guess we can do the chassis here. So we're probably going to want to do a similar thing, right? I made many different ways that we can control the chassis. When I did this code lab with Goss a couple of years ago, we did like writing one from scratch, doing a P controller or PD, whatever it was, doing smart motion, which I always recommend if you can do smart motion, motion magic, trapezoidal, that you always do that. So let's just jump into that. We'll just skip the first two guys. So trapezoidal motion profile, what's the first thing that I want to try to get right?
KF.
I want to get my velocity tracking. Yes, so KF would be the dude to do that. So I've got a little guy here, so I can say how fast do I want to go. Let's say I want to go 5 feet per second. That is this in meters per second. So I'll have that be my velocity goal. There we go. So there's some stuff happening because similar to the elevator, I'll talk about this real quick. This past year, for the first time, first provided a tool called SysID, which allows you to run some empirical tests on your robot and generate stuff like the gravity constant that we calculated by hand before. It runs your motor one way, then the other way, once at a constant speed, once ramping up speed, and it works and does fancy math behind the scene to like calculate with math what the gravity offset would be. And you can run that on anything. You can run that on a shooter, on a chassis, on an elevator, what have you, and it will spit out relevant constants based on what it measured for your robot. So with my super wonky robot, whatever constants it measured apparently give it a little bit of velocity, even when we don't have anything set. So that's just basically what's going on here. And Logan was asking before about like, what about KS and KA and KV? Those are all numbers that SysID gets you from measuring it from your robot. So long story short, this orange line is here because the compensation for static friction in the wheels is too high. But anyway, so yes, first thing we want to do is KFF. So there should be a chassis velocity KFF. Always easy to start at a nice round number. Okay, so what do I got to do?
Lower it.
We will do, I'll do a 10th this time, see what that does. All right, what do I got to do?
You'd want to raise it down.
And now?
Lower it again.
And again. That's too much, so we'll split the difference. Now imagine doing this one, right? The robot's probably in the ocean right now based on how fast it can drive. So this is one of the ones that in real life, it's annoying because you got to, hopefully you have enough space that you can let it rip for a while. Otherwise you got to let it drive 5 feet, roll it back, drive 5 feet, trying to figure out what this should be. Which is which? It's a tiny, tiny bit hot right now. So I'll do 4.5. Still a little bit hot.
Is there a reason why you're changing?
I'm changing the wrong thing.
Gravity
Yep.
composition speed.
Very easy to make that mistake. Thank you. We do that all the time. That's another thing. When you do these preferences, once you find a number that's good, I highly recommend that you back it up because we lost whatever our elevator constant was. Ooh, that looks right on the nose. So let's try it from scratch. That looks pretty good. Let's try going at a faster speed. So if this is, what was this? 5 feet per second. Let's see what it does at 8 feet per second. Can it still keep up? So it lags a little bit now. And quite frankly, there's not much we can do about that. So we could retune KFF, whatever you want your primary driving speed to be, like for autonomous mode or whatever. I recommend that you tune your KFF around that. So if you plan on driving around at 7 feet per second, why bother focusing on tuning it at 5 or at 10 or whatever? Whatever your primary max speed is, I recommend doing it around that and hope that P will take care of it when you go to one of these faster or lower speeds. So like we could potentially retune this here. And then maybe split the difference if we wanted to like average the two of them or whatever. Also, what's the delta here? A little over 0.1. So 10, whatever. It's pretty close. It's close enough for me for right now. Okay. And that's just feed forward. What am I talking about? So yeah, let's add P. Boom, fixed. Or fixed enough. It loves hitting that 1.5 dead on the nose. And that's all pretty good. So now that we have our velocity good, we should be able to do the trapezoidal motion profiling good. It should just work explicitly. So I have a driving straight command. I'm also going to bring the robot back onto Earth. So cool. So if I run this, now we should see a motion, a trapezoid happen here. It's apparently going very slowly. And it's oscillating a little bit. I blame a lot of that on the simulation constants that I'm using to make this robot absolutely impossible to drive. But it's a little bit hot. I don't know how far it's actually supposed to go, this far, whatever that is. But it's doing its job. Let's make that faster. Yeah, let's do it. So we should see the same thing. So without changing my constants or anything, it can work at that slow speed. It can work at this fast speed. Oh, and it didn't even take effect my speed limit. Looking pretty good. So this is, if you need to shave seconds off your autonomous mode, you definitely want to be using this trajectory motion profiling stuff. And now I didn't mention this that much, but First also provides a nice method to drive pads, 2D pads, where you're moving around left and right and up and down. Which is complicated math with a tank drive, but they just handle it for you. So let's see if we can do this S curve. So what I expect to happen is for it to go up and do a little turn and then finish up. So, So it ended a little bit crooked, but I know what it was supposed to do. Basically what it did, ended a little bit crooked. Let's just for posterity say, let's see how good it does without feedback. So let's get rid of our KP and see what happens. Not as good, but that's without reading a sensor at all. It still did the translation part. It didn't finish its turn all that well, but without even looking at the encoder, it did kind of what we wanted it to do. Neat. Any questions on this so far? I might actually call it a little bit early tonight, because I got through most of the things that I wanted to get through. So we went through velocity PID controllers. We went through position PID controllers and why it's way cooler to use trapezoidal motion profiling. And then we just spent a bunch of time tuning them. I encourage you, if you're interested, you both have it cloned and have it maybe not running right now, but can run it. Try to do better than we did today if you want to play around with it. Because it's kind of fun, especially when you're not worried about breaking something physical or having to go chase the robot down and bring it back to a starting spot. So is there any questions or any things that you want me to go through a little bit more?
Yeah, I would like to see how you set up all the properties.
Okay, so like I mentioned, we have a little library around it. You can just rip this code as is. I left it in our namespace, but just you can rip it, rename it. I don't care if you steal it. Steal from the best, invent the rest. So under the hood, it's making a call into the preferences API. So this is coming from WPI lib. So you can ask preferences for, you can get a double, a Boolean, whatever. You can also put it to overwrite it. Although apparently that's deprecated. You can set it, set or get stuff from it. But we put little convenience wrappers around it. This thing called an I property we gave it. And the reason that we did this is the preferences are nice because you can tune them from the smart dashboard. They live on the robot, so you have them across power cycles. If you have a robot and a practice robot that are tuned slightly differently, you know, by storing the your PID code on the individual robot, like you could tune this one, you don't have to worry about using the same values for both of them and whatever inconsistencies that bring. However, the first year that we did this, our file got corrupt in the middle of a regional and we lost all of our constants. So we wanted an easy way to switch it from being configurable versus not configurable. So the way that we interact with this, it's a member, or it's a class, it's an object, right? And when we create it, we can say, if it's constant, it's just going to use whatever this value is. If it's not constant, it will use this as a default, but then we can change it from the network tables. That way, once we got something tuned and locked in, I can go in here and say, okay, in reality, it's 3.14 or whatever, right? And then I'll switch this to no longer be tunable. That way, if our preferences save file gets wiped out, we have it persisted in code. All of that to say, it's all using the preferences API under the hood. So that's a basic property. Basic iProperty could be a double Boolean, whatever. We also, simply just for convenience, we have a way to bundle PID, motion, magic stuff all together. So under the hood, it's using the properties that I just talked about, but you can add PIDF, speed limit, acceleration limit to all of it. And it's only going to show a property for what you have added to this builder here. So like in the shooter, I'm in the elevator right now, but same idea. If you wanted to add D, you could just do this. You can give it a default value, or you could just say 0 and I'll tune it later. And then similarly, I can mark all of them as read-only here, or all of them configurable by just flip-flopping this guy around. So again, just to be clear, once you lock them down, update all your default values here. So it's actually 0.1, this is actually 0.005, and then lock this guy down so you can't accidentally lose them.
All right.
Does that sort of make sense?
Yeah, it does. I see that you have a rev PID property stuff, but do you have CTRE stuff as well?
Yep.
Sweet.
I probably didn't copy it into this project, but it exists in our mono repo.
All right.
I really wish they had the same freaking API. That would make it trivial. But no, they got to name everything different. Yeah, here you go. Here is the CTRE version.
Sweet, thank you.
They're super handy. It makes tuning stuff go so much faster when you don't have to like redeploy code. Redeploying is a lot faster than it was even just 2 years ago, but it's still nice to not have to redeploy at all.
Yeah, and like in LabVIEW, we did have like on the front, the front panel, whatnot, we did have nice things that we could easily tune and set default values, but now we don't.
Yeah.
So, this makes it nice.
Mhm.
They work kind of the same way.
Mhm. Anything else? Raphael, you all good?
Yeah. As I'm kind of like new to all of this,
Yeah, and
it's a lot to take in.
yeah, we are blazing through everything, right?
Yeah.
Sarah's 3 classes, if you were there, is like 1 full year of what you would learn in school packed into 3 days, 9 hours, right? And then this as well is just a fire hose of information. But the nice thing about these code labs and the fact that we have these videos is you can always come back to it. You can use it as an example if you're writing your code in January for how to tweak things around. I tried to cover as many bases as I could when I originally wrote this. We skipped a couple of things that I taught the first time, but when I did it the first time, it was spread over like 3 or 4 meetings. So plenty to look at. I didn't write up all the instructions like I did for the first code lab we did on Monday, but I intend on doing that. I didn't have time to put it on the docs website for tonight. But yeah, and like I said at the end of last meeting, any questions you have, always feel free to reach out to me. I can't be there on Sunday, but the next whatever time that there's one of the Sunday shoot around meetings, I'll be happy to show you how to do this on an actual physical robot and why it's harder, more annoying, but more rewarding to see, if nothing else.
Yeah. But yeah, I definitely think like after a year of experience and just being able to look back on this, it'll start to make more sense.
Mm-hmm. Yeah, a lot of it is practice, especially just the general Java semantics and stuff. So
Mhm.
oftentimes when a kid's coming back for year two, they like learned whatever I couldn't teach well the year before in school. Like, oh, it all makes sense now. So you'll pick it up eventually. It's absolutely okay if it's not clicking today.
Well, thank you very much for
Mhm.
the workshop. I'm gonna head
Yep.
out.
No problem. So I think a guy from another team is doing the Git tutorial on Friday, if you're interested in that. Ashley might be able to show you stuff on the robot on Sunday if you go. Depends on how much gets wired between now and then. But otherwise, I'll keep you guys posted if I'm doing anything else.
Okay. Thank you.
Thanks for coming.
Bye.